Welcome to Casting Academy. Today we are going to discuss about the theory of simple bending of beams. When a beam is loaded with some external forces, bending moment and shear forces are set up. Beam loaded with some external forces, the bending moment and shear forces are set up. The bending moment at a section tends to bend or deflect the beam. Bending moment deflect or bend the beam, and internal stresses are developed to resist bending. These stresses are called bending stresses, and relevant theory is called theory of simple bending. The simple bending or pure bending. If a beam bend or deflect only due to constant bending moment and not by the shear forces. A beam bend or deflect only due to the constant bending moment, not due to shear forces, is called pure bending. Just we are discussing the theory behind the simple bending. As you see the beam cross section, here the dx is the small length, the bending moment acting here, AB considering the topmost layer of the beam and CD is the bottommost layer. So after bending, the AB is contracted to A dash B dash and CD contracted to C dash D dash. Here the layer EF is not change in length even after bending. So this is the idea behind the theory of simple bending. So the length of all layers are changed due to some are shortened, others may be stretched. The layer EF neither shortened nor stretched. That is called the neutral layer or neutral axis. Assumptions made in the theory of simple bending. Number one, material of beam is uniform throughout its length. Material of the beam is uniform throughout its length. And as number two, beam material has equal elastic properties in all directions. Material properties are equal in all the directions, and beam material stressed within the elastic limit and thus obeys Hooke's law. The beam material stressed within the elastic limit and obeys the Hooke's law. Beam material say has same value of Young's modulus both in tension and compression. The same Young's modulus both in tension and compression. The radius of curvature of the beam very large compared with the cross-sectional dimensions of the beam. The radius of curvature of beam very large compared with the cross sections of dimension of the beam. The resultant pull or push on transverse section of the beam is 0. The resultant pull or push in transverse sections is 0. Each layer of beam is free to expand and or contract independently of the layer above or below it. Number 8. Cross section of beam which is plane and normal before bending will remain plane and normal even after bending. So these are all the assumptions made in the theory of simple bending. Neutral axis. As you see the layer EF, this is called neutral axis. The line of intersection of the neutral layer with any normal cross section of beam. What is meant by neutral axis? The line of intersection of the neutral layer with any normal cross section of the beam. That is called the neutral axis of that section. No stress of any kind at neutral axis. Here the no stresses are developed in the neutral axis. As you see the bending stress distribution, this is called the neutral axis. Here this line is called neutral axis. Above the line is compression stress and below the line is tensile stress in case of simply supported beam. As well in cantilever beam the tension stress are acted upon above the neutral axis and below compressive stresses. So this is stress distribution in bending stress distribution in simply and cantilever beam. Moment of resistance. The maximum bending moment that a beam can withstand without failure. That is called moment of resistance. The capable of maximum bending moment before failure. That is called moment of resistance. The compressive stresses and tensile stresses form a couple whose moment must be equal to the external moment m. The Fc and Ft form a couple whose moment equal to the external moment m. The moment of this couple which resist external bending moment is called moment of resistance. The moment of this couple which resists the external bending moment is called moment of resistance.